In this video, we're going to talk about the average value of a function, not just over a discrete set of objects, but in this case, over a continuous region or volume, which is going to get a little bit tricky, but not too different from what you might expect. So generally speaking, the average value of a function, or of just anything really, is you take the sum of all your things and then you divide by the number of things. Now, if we're in a continuous setting, we can't always do that. But you might remember in Calc 2, for example, that you can still find the average value of a function over an interval by, well, how do I add up everything on an interval? Well, that's essentially what the integral does. So you can find the average value of, say, f of x by taking the integral of a to b of f of x dx. That's kind of like adding up all your things. And then instead of having the number of things, we divide by the length of that interval, which in this case is b minus a. And this exact same idea is going to apply here. So if I'm in a 2D case, if my domain is, if I'm looking at the average value of a function over a region, then all I need to do is set up the double integral over that region of my function. And then I need to divide by essentially the area of that region. And one way to represent that is just by taking the double integral of the function 1. We don't always need to write that one, but here I did. And in the 3D case, it's incredibly similar. We'll just have the triple integral of my region, or of, we'll say, we'll use R. Why not? W. W is what I use. We'll use W of f dv all over the integral of w dv. So now we're going to look at an example. We're going to set up an integral to calculate the average value of x squared on the unit sphere. So what am I going to want to do? I'm going to want to integrate. We have a three-dimensional region we're integrating over. So I'm going to be integrating over the sphere, we'll let w be the sphere, of the function x squared dv. All of that over the integral of w dv. Now, okay, that's a little lazy. I wouldn't actually be able to calculate this. I would need to do some work. And one thing I could do is I could, figure out what my bounds of integration are for the sphere, or I could change to spherical coordinates. If you remember, when we do this change of coordinates, then we need to use the Jacobian, but we kind of have a nice little thing that we just remember for when we're changing spherical coordinates. Our Jacobian is going to essentially end up just turning into rho squared sine of phi. That's what's going to amount from using our Jacobian there. So let's go ahead and actually see what we have here. So x squared, what's x? Well, we know that x is going to be rho sine of phi cosine of theta squared. That was very messy. And then we're going to have rho squared sine of phi there. And then we're going to integrate. It doesn't super matter what order we integrate, I guess, but I guess we can do d rho, d phi, d theta. And if we think about it, rho we're going over the units circle, so we're going to go from a radius of 0 to a radius of 1. Then phi, we're kind of dropping from the positive z-axis to the negative z-axis. So that's going to be an angle of 0 to an angle of pi. And then we're spinning all the way around the z-axis for our theta values. So that's going to go from 0 to 2 pi. So that's our numerator. And then we're dividing by, well, a very similar thing, except instead of having this row of sine of phi cosine of theta in the middle, we're just going to ignore that. And we'll just have rho squared sine of phi d rho d phi d theta. And actually, we can simplify this even more. We can skip a little bit of work. I can't really do all too much to the numerator, but we'll go ahead, at least combine some stuff together. We're going to have rho to the 4th. We're going to have sine cubed of phi. And then we're going to have cosine of theta. D rho, d phi, d theta. That's all going to be divided by, well, I know the volume of a unit sphere, which is what this is. That's just going to be 4/3 pi. So if I had the patience to calculate that, that would give me the average value of this function over the unit sphere. So just to recap what I did, is I integrated the function that I was interested in over the region that I was interested in. And then I divided by the area or volume of that region, depending on what dimensions we're in. And there you go. That's how you do an average value problem.